In this video we're going to take a look at hydraulic valves. This is part A of 2 parts. So one of the things when we're dealing with hydraulic valves is hydraulic oil is acting on a component to do something for us, whether it's to relieve pressure, to control pressure, to divert pressure or flow. So if we keep that in mind when we're taking a look at valves, and again, number one is look at a schematic and understand what that schematic is doing for us. So again, one of the things we see in a lot of these valves is we will have a spring, an adjustable spring. As pressure builds against piston, the spring counteracts that force. Now again, if the hydraulic pressure is higher than the spring pressure, it's going to compress that spring to a point where maybe it opens a port and allows that extra pressure to be dumped out so that we don't exceed the pressure rating of the system. It could be to control the pressure. So we have to take a look at what the schematic shows us and interpret that properly. So let's take a look at the first schematic and valve. So if we take a look at the schematic, we can see that oil is flowing straight through and off to whatever component it's flowing through to. Now we also see that we have a pilot line, so we know that it's pilot operated. So what happens here? So as pressure's coming through, and for instance, let's say it's dead-ended, we have an adjustable spring. We also have a drain that goes out to the reservoir. Now as pressure starts to build here, and if we take a look at the picture, pressure flows straight through, but there's also a pilot port. Now pressure goes under and acts on the bottom of the spool valve. As the pressure increases, pressure underneath, because the surface area is larger underneath, will start to compress that spring. Now once the pressure underneath exceeds what the capacity of that spring is, this port's going to close off. Now why do we have a drain? Well, what would happen if the pressure up on top was the same as the pressure underneath? We'd also have spring pressure up on top. This valve would never close off, it would never shut. So we need that drain to drain any oil that's slipping past this spool to go out to drain, so that there's zero pressure in here. All we have is the spring pressure. So this valve is normally open, and at a certain pressure, whatever we have it set at, this valve will close off and prevent any more flow. Now we can use this, for instance, in a pilot operated system where our pilot system runs at 300 psi. At 300 psi, this valve is going to close and not allow any more pressure through. Once that pressure drops below 300 psi, the valve will open again and allow more pressure to go through. So again, as that pressure underneath gets to higher than the spring pressure, then that valve is going to close off and no more pressure can get through. We take a look at this valve, and again, this is a normally closed valve. Looking at the schematic, pressure comes in, it can't go through because it's shut off, but we also have a pilot line that feeds underneath. And the same thing, we have an adjustable screw tension, so we can change the resistance on the spring, and we also have a drain that goes back to the reservoir to bleed off any pressure that gets on the other side of the spool. So what happens here is inlet pressure comes in, it acts on a surface area, it can't go anywhere. But once the pressure in here exceeds the spring pressure, it's going to open. And what is this good for? Well, it's pressure relief valve. We'll see these, they're quite common to have in every system, whether it's a circuit relief or a system relief. They're pressure relief valves. They're going to relieve pressure beyond a certain point. So again, as the pressure builds in the pilot system, it's going to start to lift that spool valve. Once it lifts the spool valve to a certain point, it's going to open this outlet port and allow that extra pressure to drop. One thing to remember, let's just say that this relief valve is set at 2,500 psi. This spool valve is going to maintain this inlet pressure at 2,500 or 2,499. As soon as that pressure drops below that, the spool valve is going to shut off again until that pressure rises. The pressure in the inlet port never drops to zero. It'll always maintain that pressure. Now we take a look at different types of springs. Now we see lots of different types of springs that we have. These are constant springs or constant rate springs, which means that if we take a look at the very first one, if we deflect it 1 inch, we have with 100 pounds of force. To deflect it 2 inches, we need 200 pounds of force. Again, when we have a constant rate spring and a variable rate spring, we're going to use constant rate springs in all of our valve systems. Variable rate springs are a little different, where we have to increase the weight to get the same amount of movement. So for instance, if this was a variable rate spring, if it took 20 pounds to move it 1 inch, in a constant rate spring we'd need 40 pounds to move it 2 inches, but in a variable rate spring we may need 50 pounds to move it 2 inches. But we're only going to deal with constant rate springs. Now, when we're taking a look at a relief valve, pressure override is also a relief valve. Inlet pressure comes in and acts on a surface area. As that pressure starts to increase above spring pressure, the valve is going to open. That's cracking pressure. Now this may, let's just say again, we're working with 2,500 psi. At 2,501, this valve is going to open like this. If this pressure in the system stays at 2,501, that valve is going to open just a little bit. But let's say the pressure increases quite a bit more. Well, then we're going to get full flow pressure and dump any extra pressure out of there. One of the things we've got to be aware of is anytime we're running in relief, it's oil squeezing through a small area and we're going to generate heat. So we never want to run in relief for a long period of time, because we'll overheat the oil. Now, 3 types of relief valves that we're going to see. The ball style, and we looked at this one earlier. As pressure comes in, it works on the surface area of a ball. Poppet style, again, as pressure comes in, it works on the surface area of a poppet. And guide poppet, again, same thing, is when pressure works on a surface area here. So really, when we deal with any types of valves, again, it's pressure working on a surface area, but it's opposed by a spring pressure of some type. Now, a pilot-operated pressure control valve in a system. So again, pressure comes in, works on a surface area. Now, it works on this poppet to begin with, and what happens is, as the pressure starts to increase, the poppet's going to open first and allow that extra pressure to be dumped out. Now, if that pressure gets to a certain point where this isn't capable, it's too high, then what's going to happen is this main poppet's going to open and allow us to dump that extra pressure at full flow. Now we're going to deal with 2 different types of systems later on where our main relief can handle full flow pressure and it doesn't overheat the oil. And then we're going to take a look at some older systems where the main relief can't handle it and it tends to overheat the oil. So looking at a basic schematic, again, we have our reservoir, we have our pump, and this is our system relief valve. Now, I talked about system relief valves and circuit relief valves earlier. So a system relief valve is set up to relieve the whole system. A circuit relief is set up just to relieve a certain circuit. Now, for instance, in a bucket, we can have a circuit relief on each end of the cylinder, and that would be incorporated into the valve. Or we could just have one. But if we only have one, how does the other relieve itself? Well, it uses the system relief. So let's just say that when I want to roll my bucket out, okay, extend the cylinder on the bucket, the pressure on the extension is 2,300, where when I roll it back, 2,300 isn't enough. I want to have 2,500. So it will use the system relief on the rollback, but it will have a circuit relief on the roll out, on the tip out for extension. So again, it all depends on the application that we want. So what does the control valve look like? Well, when we take a look at a control valve, this is two valve bodies plus a main body, and this would be our inlet. So this is an open center system. So if we go back to this picture again, it's an open center system, so oil can flow through both of these control valves and then return back to the tank. So what we have is we have a system relief, and again, the system relief looks after everything that a circuit relief doesn't. So if this, for instance, if this valve body here wants to use the system as a relief, this will be a dummy plug, so the system relief will control it. But both of these here are circuit reliefs, so when we pull back on the control, this circuit relief is going to look after this one, and this circuit relief will look after this one. And we may have circuit reliefs on the other side. So again, system relief valves are set up in the circuit, so if the pressure does exceed what we want in the system, then it's going to dump that extra oil back to the reservoir. And taking a look at how the circuit relief works. So the working port goes out, so this goes out to whatever implement we have. As pressure acts on a poppet in here, we have a spring in here, and pressure is acting on this poppet. As it pushes that poppet off its seat, oil can flow from here and then back to the return side. We also have what's called a makeup valve in the system, and we'll see how that works a little later. How do we set relief valves? Well, adjustments can be made with either adjusting screw like we see here, or on some systems we may have to add or subtract shims to change the adjustment. This one here is a lot easier. So anytime we're going to be adjusting it, we don't want any pressure on it. We don't have to shut the machine off, but we don't want to be putting that component into a relief position. So what we're going to do is, first off, is we're going to hook a pressure gauge into the system on whatever component we're setting this pressure gauge or this relief valve for. Then what we're going to do is we're going to dead end a cylinder. We're going to watch it, see what pressure that relief valve is set to, and adjust it accordingly up or down to what the specifications require. Never exceed the specifications of what the relief valve is set for. If for any reason the component isn't, let's say on the bucket rollback again, say it isn't rolling the bucket back like it should, check the relief valve pressure. If the relief valve pressure is right, then there might be something else in that system that's causing it not to work properly. So don't exceed what the manufacturer recommends for that relief valve setting, because if we do, we could blow a hose or a cylinder. So be aware of that. Now, when we're bench testing a hydraulic valve, we can use a portable pump and pressure it up and check what our circuit reliefs are. So again, in here we're going to have a system relief valve, but each of these circuits will have a circuit relief valve. And again, if this uses the system, as we pressure it up, whatever the system is set for, we can set this up at. Now you're going to see some circuits again that don't have a circuit relief, and they will use the system relief. Now, when we're taking a look at what are some of the problems that could happen, again, we have an O-ring and a backup ring. Now, the backup ring is there to support the O-ring. If that's missing, the O-ring can actually, with pressure, be forced out and create a bypass. So again, oil is coming in through the inside of here and acting on this poppet. Once it pushes it off its seat, oil will flow out here. But again, with a damaged O-ring, it can flow past, so we would never be able to reach what our relief valve pressure is set at. So if it tends to want to relieve too early, we could just pull these relief valves out and check the O-rings. Again, if we're doing that, a couple things to make sure we do. Number one is ground all our equipment and shut the machine off before we pull it out, so that there's no oil is going to come out of this, because remember, a lot of these systems are open circuit systems, so it's flowing all the time. As soon as we take that out, it could come out. So just be aware of that when we're working on a system. Now, a closed center system is a little different. So what we have is we have our pump and we have our unloader valve. Now, an unloader valve again is a relief valve. We have a one-way check. Now, what happens in a case like this is pressure starts to build. It goes through the one-way check. It goes into our accumulator and it dead ends here. And what happens in this system is if we're not moving anything, this relief valve or this unloader valve can handle the flow of hydraulic fluid without overheating it. And it's going to go back through the filter and return into the tank. Now what happens as soon as we see a pressure drop in the system through this pilot line, this valve is going to close off and we can use our implements. As soon as we stop using our implements, pressure is going to rise in this pilot line and it's going to shut off, or it's going to open the flow and allow the flow to return. So using a positive displacement pump in a case like this, where we have an unloader valve that can handle the flow rate. And why do we have a check valve in the system? Well, we need a check valve so pressure can't go back through the system and dump the pressure out of the accumulator. We also talked about a load check in the system. So let's just say that our system pressure is at 2,500 psi. This check valve will maintain that 2,500 psi when this valve is open. What's the pressure in here? Well, it has to be 2,500 psi to open this and allow that flow to return to the tank. So how does a pilot operated system work? Well, looking at the valves, again, there are many manufacturers of valves, but understanding how they work is essential. So here again we have pump pressure coming in, going through the one-way check, charging the accumulator and going out to the system. Now once this pressure, again, let's just say it's 2,500 psi, once this pressure in the system builds to that pressure, it's going to lift this piston off of its seat, and when it does that, it's going to dump that flow back to the reservoir. And again, it's going to stay in this position until the pressure drops. Once the pressure drops in the system, this will go back down and it will go into the closed position, and that pressure is going to go out. So tandem hydraulic systems. So if we have, for instance, a motor that runs 2 hydraulic pumps, we may have a check valve in the system. So pressure can go out here, and until the pressure in this line here opens up this port here, nothing happens. Now it might be that this one goes to another set of controls. So for instance, if we have an excavator, we may have 2 pumps in the system. One pump runs one track, one pump runs another track. Or it can divide the circuits because maybe the pump itself isn't big enough to supply when we're running everything. So we need both pumps. And here again, when we're doing troubleshooting, it is identifying which pump it may be. So we're going to have 2 separate circuits. This is why it's really important to understand schematics and read schematics. If we have everything failing, then the problem could be in the circuit dumping somewhere. But if we only have half of the circuits that aren't working, and we can identify that's pump A or pump B, then we can look at that system and see where the problem might be. It might be that the pump is failing. And we can go in and then we can do a flow test on the pump. And we're going to go through flow testing a little bit later. Pressure reducing circuits. So a pressure reducing valve again is going to limit the amount of pressure that's going out to the circuit. So here we have our pressure reducing valve, and we can tell it's pressure reducing because it's normally open and it's our pilot line on the other side. So once the pressure gets to a certain point, it's going to shut this off. So why is that important? Well, let's just say that we have a processor and I want to control the amount of clamping force that I have on my arms that hold the log, because again, I don't want to crush the log because I can damage it, but I want enough force on there that I can hold the log and use a saw motor to cut a log to a certain length. So we're going to have a system set up so that first thing we want to do is it wants to clamp the force, again, path of least resistance. We want to be able to clamp the log and then saw it. We don't want the saw to work before it clamps, because if it moves, it'll bend the saw blade. So we may even have a priority system in there where until this pressure gets to a certain point, the saw won't operate. So this is a pilot operated pressure reducing valve. Again, we got pressure coming in, goes all the way through. Once pressure builds on this side, it acts against a spring, and what will happen is it will close off and prevent any more oil from going through. Sequencing valve. Now, I just talked about this on a clamping cylinder. Again, a sequencing valve is set up in a system so we can have a sequence of events happen. Number one is we want the clamping cylinder to clamp the log before the saw moves. Or maybe we want one cylinder to dead end and the pressure to build before we want another cylinder to move. So we can use that with a set of sequencing valves. And again, how they work is pressure is going to come in. Once the pressure on the cylinder equals or goes to the limit that we want, then this valve is going to open and allow pressure to go out to the motor. Now this is looking at a direct acting sequencing valve. Okay, pressure builds here, works on the surface area against spring tension, and again we have a drain at the top because we don't want pressure up there or this piston won't move. Once it gets to a certain point, then it goes out to the secondary function. Where we might also see this is in a priority system. For instance, any of the systems that use a priority valve, our brakes and steering take priority over anything else. Once that condition's been met, the priority valve will open and allow pressure to go to our secondary functions. Now, there's another thing called a counterbalance valve. Now, a counterbalance valve helps prevent a load from falling as we open up a control valve. So for instance, if I don't have enough pressure coming out of my pump, and let's just say I have 2,500 pounds of load on here, as I open this valve at the bottom, if I didn't have this counterbalance valve, this load would drop a little bit to begin with, then it would start to lift as the pressure came up. Well, what this counterbalance valve does is it protects the system. So as the pressure is building in the system, it goes through this one-way check and then goes out and lifts the load. Now, what happens when we want to go the other way and force this down? Well, it can't get out this one-way check, and the pressure underneath on this pilot line has to be sufficient in order to open this and allow it to go back and return to tank to our load to go down. And this is what a counterbalance valve looks like. Again, it's just a spring and a spool, and it's pilot operated, so we have a pilot line underneath, and we looked at one of these valves a little bit earlier. So a lot of the times when we're dealing with pressures and surface areas and what we can do with that. Now, we've already discussed what happens when we increase the pressure on a big surface area, how much force we can get coming out of it. So again, if we take a look at how do we calculate this, well, Force equals pressure times area. So how much force? Well, if we have 1,000 psi on an area of 10 square inches, what are we going to get? 10,000 psi? Or 10,000 pounds of force? Okay, another type of valve that we might see, we see these on cranes. And again, it's to prevent the load from dropping as we start to move the controls. And here what it does is the same thing as we discussed on a counterbalance valve, is the pressure underneath. Say we have to lift the load. We don't want that load dropping for a split second. We want to be able to lift it under control. So what has to happen is the pressure on the opposite side has to equal the pressure for the load in order for us to lift it. And this valve here will control that. So looking at this picture, as we're lowering it, pressure comes in here, works on the motor. Now, what prevents for lowering it? Well, what happens here is this is closed off. Pressure underneath moves this spool enough to open the return side and allow it to return. Otherwise, it's braking it, as in it won't allow it to move. So if this pressure isn't quite high enough, this won't move, because again, we always have to have return flow in the circuit in order for this motor to turn. So this is what happens when we brake. So when we let go of the controls, the pressure drops off, this spool drops down, locks this motor from turning, and it can't. So if we want to raise it, what happens then is we have to put pressure on this side, and then it has to lift this spool valve up. Again, we have to have a complete circuit in order for this to move. Another thing we see, again, it's a lock circuit. So again, we have our positive displacement pump. We have an open center system. But when I put pressure to this side here, it pushes through the one-way check, but it also goes over and unlocks the other side of the cylinder. It pushes this ball check out of the way and allows oil to flow back. Same thing when we're going in the other direction. Oil pressure can come through, but until the pressure on this side is great enough to start to lift the load, it will not unlock this lock valve, and we don't have return flow. And how that looks like in a circuit is something similar to this. So we have our piston in the center, we have our two ball checks, and as we start to increase the pressure in one side, it's going to push this shuttle over. It's going to open up this ball check and allow oil to return. And works the same in the opposite direction. Now, we talked about what does an orifice do? Well, it restricts the flow of oil. Now, what happens here is, because of a restriction, the pressure is going to build on this side. It's going to go through the restriction, and then we're going to get a pressure drop. Now, let's just say that our pump puts out 10 gallons a minute. It's a positive displacement pump, which means it's going to displace that fluid no matter what. Now, if the relief, maybe the pressure is not high enough for the relief valve to open. So as oil is coming through here, it's pushing in here at 8 or 10 gallons a minute. It's going to push through this orifice at 10 gallons per minute. And as it starts to go through here, as soon as it gets to the other side, we're going to start to get a pressure drop slowly, and then as it gets through here, if we don't have any resistance on this side, it'll create a pressure drop. And we can use an orifice to regulate flow. Now, these can be variable orifice, or they can be a fixed orifice. Now, an orifice can also free flow one way and not the other way. For instance, if I have a forklift and I want to be able to control the movement of a component, I can have it free flow in one direction but control the flow in the opposite direction. So if I want to have a cylinder so I can control it coming down at a certain rate, I can put an orifice in there that will control that. But if I want to lift it at any speed I want, then that orifice can open and free flow in the opposite direction. So again, we can have it variable where we can control it, and again, we may have an adjustment on there so we can control the flow. And how does that work in a circuit? Well, if our pump puts out 10 gallons per minute, we have a variable orifice that's going to control 5 gallons per minute. That's, again, if we don't have any load on there, we want to control the flow of this to a certain point, and it's going to dump the other 5 gallons out. But what happens as we increase the load? So as we increase the load, our variable orifice, which we can control how many gallons it's going to go through here, we can control how fast it's going to push our load, and it's going to dump any excess out past back to the return side. So how do we control that? We control that with what's called a compensator. So as the load increases to the compensator will increase and control flow through the control valve. So again, we're using a compensator valve, and it has a pilot operated system. Again, pressure has to increase in here before this will open, and it will control how fast this is going to move out. As we change the load, it's going to change at what speed this is going to move out at, because we want to maybe move this at a constant rate all the time. Bypass pressure compensating flow system. Again, here's our needle valve where we can adjust it to whatever flow we want. As the pressure comes in, it pushes against the spring, dumps any extra fluid back to the reservoir, and oil goes out to the regulated, it's a regulated flow. And again, as that pressure increases in this side here due to a load, it's going to start to block this off. And this is what a pressure compensating flow control valve it looks like. Is we can move this anywhere in here and lock it in position and control the flow. For instance, say I want to control the speed of a drum on reeling a cable, and I want to be able to either increase it or decrease it, but I'm not going to change the RPM of the engine by doing so. I can use this flow control valve, and it will control the flow at how fast that cable is going to unreel. And it doesn't matter what the pressure is, it will always unreel at, I don't know, 30 feet per minute. So we can control it with this valve. So taking a look at this schematic, one of the things we haven't looked at before is this. This is a variable displacement pump, again because the arrow we know it's variable displacement, and this here is a pilot operated system that controls a swash plate. And what we do with that type of a system is, let's just say it's an axial piston pump, and what we want to do is control where the swash plate is, and again how much fluid it displaces. So we can use this type of a system again to control the flow rate regardless of what the load pressure or changes in the circuit happen. And again, we can use this in combination with the last setup we used. And this is how it looks. So as inlet pressure flow comes in, goes out, we control this, but pilot pressure in here can open and close this to allow or increase or decrease the flow. So in this schematic here, again, we have variable displacement pump. But what this restrictor valve does in this situation here is it's a variable orifice, so we're controlling the flow to extend the cylinder, can't get past the one-way check. But when we retract the cylinder, we don't want to restrict the flow, so it goes past the check valve and then back to the tank. And here all we're doing is, instead of it being on the extension side, it's on the return side. Priority valves. Now we talked about a priority valve earlier, where a priority valve, power or steering and brakes have priority over secondary controls. So until that condition has been met, let's just say we're in a articulating machine. So pressure builds in our steering system. Once that steering system has been satisfied, then the priority valve will open and go to the secondary implements. And simply, how does it work? Well, inlet pressure comes in and acts on a piston. Once steering and brakes have been met, then what's going to happen is it's going to open this is going to shuttle open up the secondary components and allow them to be used. But what happens if the pressure in here drops? Well, if pressure in here drops, the spring pressure is going to push this back and shut off our secondary implements until this circuit is satisfied again and has the pressure it needs. Now, a proportional flow divider. So again, what we want to do is, there's a couple places we can use this. For instance, on a motor and a cylinder. We can also use it on a tailgate, where if we have all the load on a power tailgate, all the weight on one side and none on the other, we want to be able to lift it evenly, because again, the side with no load is going to want to lift first, and it will bend the tailgate. So we're going to use this type of a flow divider circuit to even out the flow to both circuits, so that they both lift at one time. And what will happen is pressure will increase on one side to lift the load, and it'll also decrease on the other side so it doesn't bend the gate. So again, inlet pressure comes in, and it's this compensator spool valve is going to move in either one direction or the other direction to compensate for the load. And that ends the first of these two series on valves.